C pipe. And lucky enough, actually, we got Andy Gentry coming on board here. Andy's able to join us. I've only been at it for a couple minutes. We got Earl, Peter, and Joe online right now. Actually, looks like we got a couple other people just popped on as well. Oh, hey, Art, good to see you. Brent Long also just popped on as well. Andy, say hi to everybody.
Hello. Where's the camera so you can see them too?
Oh, well, right now they're just doing the imaging. Yep. So Andrew Gentry then is one of our newest reps, technical sales representative and bioremediation. So he's been helping us out, marketing, branding. He's been learning as well. And Andy, we're just talking about 2015, 2016. Glad to have you on board and moving right along. Let's see. So was talking a little bit about litho, chemo, auto, heterotrophic, all sorts of stuff. What does that mean? So we were talking a little bit about if you can supply for your carbon source, your energy source, and your oxygen source, and decouple those as limiting factors, you can get a lot more treatment. So one of the things we were finding also is, as during the initial 2015 year, I had the lids off the top of these things, and there was trees up above, and things would fall in. And all of a sudden, I started seeing different morphologies. As you can see right here, there's the coir in the background and material that is settling on it. But then you look at this really almost kind of downy, almost fungal growth-like pattern that's coming off of a stick that fell into the tank. And I started looking it up, and then I was like, okay, so this is maybe then some evidence towards the difference between multiple pathways happening all at the same time, lithoautotrophs and lithoheterotrophs. Difference between autotrophic and heterotrophic is the source of their carbon dioxide or their carbon. If it's CO2, like plants, they are autotrophic. And if it's heterotrophic, they're using organic carbon sources. And looking at this, these sticks and the other material that have fallen in, yeah, here we go. So here's another couple examples. This, as we're looking here on the coir down on the bottom right side, I had initially thought that when I would pull this stuff out of the tank, when it's no longer supported by water, which is what you can see on the top left there, that it would just fall apart. Pulled it out of the tank, and it really does have these solid eyelash-like structures. And it's an iron precipitate, but it's growing farther out into the presence of more of the growth, you call them metabolites if you want to. I also thought it was really interesting that it's kind of like a toothbrush there, where are they intentionally spacing themselves out? I don't know. Biofilm has a tendency to not only encourage its growth, but is also capable of limiting its growth when in competition. And if that competition be space, oxygen, energy, or carbon, then it will actually spread itself out. I'm thinking that this is reasonable evidence towards that assumption. And as you know, as we had seen later on, that it was in fact shortmanite, different mineral forms. It's occurring in this case at a pH of about a 5.3 to a 3.8 influent. And this is during the pilot study, which is what we're looking at. And coming out of the back end of that system, then the pH had dropped to about a 3.8 to a 3.5, demonstrating the iron removal, iron oxidation, and acid production, so that the pH drops as you're going through the system, which is useful because then you can in some ways use just a pH pen to be able to determine sort of as a real loose proxy the removal rates of iron within the system, that you can say, hey, yeah, it's definitely functioning. We've got the pH dropping. And if you know in the beginning that there's no alkalinity in that water, and when I took a lab sample for alkalinity, that it was below detection, not saying non-detect, just below the detection of the lab for presence of anything like calcium carbonate or other buffering agents that would be seen as the alkalinity. Now in study 2, it was done mostly during the summer time, and the pH was actually, I believe it was higher overall than what was coming out during the winter. I believe that this is directly linked to the saturation and the temperature, dissolved oxygen saturation in the water between the two different times of year, and that during summer, when the water temperature is up around 60-something degrees versus 35, 40 degrees, you get enough of a difference of oxygen saturation that it will affect the rates by which oxidation actually occurs. So here we got, I thought this was really neat. No, that is not some kind of a deer hoof. That was a piece of, I think it actually thrown that stick in after I saw some of the first material, first iron coming out on another stick just to see what would happen. And it, once again, the very lines that are showing up and just almost that spackled pattern, I think maybe additional evidence towards biofilm controlling the precipitation upon the entire chunk of wood there, where they're actually giving themselves some space so that they're actually limiting some of their own growth in order to increase in certain areas to increase their growth in other areas. It's what I believe we're seeing right there. Let's see, it already talked a little bit about, so that's once again going back to the first study, then you got step by step by step. So we'll look at some data next, sample points. So you got one sample point way up here in the by the seep, and that's about 60, 70 feet worth of delivery line. And then I took sample points from the top of each one of the MRUs, and then of course there was the effluent, but since they are bottom up flows, back end of this pipe is the same thing as the top of this water right here on the third cell. So talking a little bit about the data. Now I'd set this up in, boy, I guess January, or yeah, I'd set this system up in November. Didn't sample. This one was self-funded, so I was trying to be a little frugal on the funding because we had to pay for it ourselves. And boy, I was pleased as punch when the first couple samples, which are every, let's see, we had over about 2 to 3 weeks. We go from influent, which is up at the first pipe, 68.4. By the time we got out of the third cell, you've got a 19, that's milligrams per liter, by the way. That's a 19 milligram drop. Next week, come back, hey, it's looking even better. We go for, and this is for all 3 cells then. We combined the whole thing just to make sure it was working before we started doing more detailed profiles on, this cell, this cell, this cell. And in the second week, then we're going from 78 to a 43. pH is dropping. Iron is precipitating within the tanks. And then, of course, we get up to our third sample set. The iron continues to go upward to 78.1 milligrams. And out of the back end of the third cell is a 37.6. Now, this is 4 gallons a minute. That's good treatment rate for not that many actual systems. Not too many are running at 4 gallons per minute. But and we'll talk a little bit more about the higher rates that we get into in the second study. But one thing I do want to point out then is we go from 119 to 316. We got a 2-month jump there, almost full 2 months. So that this system has been operating for 4 months without me touching it. I didn't stir it, I didn't flush it, I didn't drain it, didn't do anything. And by the time you get down to 316, treatment rates are really falling off. Well, what's going on? And then 321, hey, look at that. The back end, it actually jumps back up again. And then you get on 414, you wait almost another entire month and you're still getting good rates, but it's nowhere near the removal rate of what we'd had on, say, 119. And it especially starts getting, the treatment rates are getting worse as you go into April, mid-April, to the point where on getting into May 526, where water in to the second cell is, or the concentrations are even higher than they were going in. It was time to clean the system out. That's been the broad-based determination that if you start seeing where you're getting a major drop-off in treatment within an organic matrix, 3-dimensional matrix system like this, you should have cleaned it out about a month ago, 2 months ago in this case. And that's what that means. It isn't that the system failed. It isn't that anything catastrophic happened. It's just, no, there's your maintenance routine. And it gives you an idea. It's like, okay, I have to come back. Now I know this system requires at this volume with this loading and this flow rate requires, say, 6, 8 cleanouts, draining and flushing per year. It's actually pretty simple. No problem. We can deal with that. And then, so we, the demo system worked out, the pilot system worked out really well. And you can see it actually here in the background. And we decided to go on to 2 true MRUs. One's using weirs and vaults and a much higher rate of flow through. Now the overall flow on this system, total flow, was somewhere around 100 gallons a minute. So when we're taking off 4 gallons a minute, it's a drop in a bucket. But with this, the true MRUs, we were able to run this thing up to around 70, 80 gallons a minute at some of our best rates. or some of our highest flow rates. And as it turns out, right around 60, 65, 70 gallons per minute is actually the flow rate you want to run one of these systems at, because dissolved oxygen is one of the primary limiting factors within this system. And well, pretty much in all metabolic systems, you think of an aerobic wetland, if you start cutting off your ability to be able to satisfy BOD and COD, you're going to slow down your treatment rates. And so increasing the treatment rates, it's counterintuitive. You actually want to run these systems faster for the most efficient rates of treatment. So here you can see on study 2, that is a coconut coir there, and those are individual strands covered in about 1 inch thick worth of Schwertmanite. So over time, the entire cell will fill in and go into, I'm not sure if the proper term is plug flow, but one way or the other, that the unit then, or that cell begins to plug up, and it increases the pressure, the hydraulic pressure going through that unit, but that's okay because it backs up and it's got weir overflows. And the reason I wanted, and in this system, that first cell should have been cleaned out a couple weeks ago. I wanted to show that it's okay if it does begin to plug up and go into the overflow, because we got it covered. We've got plans for that, and it's other weirs, other means for the water to be able to be delivered through the system without flowing over the sides. And that's why I wanted to show the water backing up, but it allows you to go up over the top of those backup weirs, so you don't have any issues. You're not going to have some breakthrough going over the sides. So for the second study then, so 526, just as we got the coir, the system started, that's fresh virgin coir, never been used for anything before, and don't really have a whole lot of treatment in the very beginning, and that was put in on 526. That's when the water was turned on. And then coming back 2 weeks later, we're going from 74 down to a 59, and that's milligrams per liter. Now in this case, the green bar, by the way, that's your flow. So 35 gallons per minute. Now we come back a couple days later, and it had turned out that there were some leaves plugging the influent up at the top end of the system. So went from 35 gallons a minute, removed the leaves. If I'd had some kind of a suction filter, it would have taken care of the problem. Jumped up to 75 gallons a minute. Now we're removing about 71 milligrams down to about 61 milligrams. So it's not quite, you've got a little more than double the flow rate, and you have just slightly less removal. We're going from 70, we've got about 13 points, 14 points, we've got about 10 points at 75, but that's more than double the flow. So that the actual loading that you're removing at that higher flow rate is more efficient considering the residence time. And then moving on to 627 and 76 down to 64 is 12 points at 55 gallons per minute, a little bit slower, pulling out just a little bit more as far as the overall, or as far as the concentration goes. But again, that's lower loading removal rate. So the actual efficiency is a little bit lower. 629, 46 gallons a minute, and we're looking at about 11, 12. And then we go into 8.2. Now we're getting back into the points where we have about 2 months, haven't done any kind of maintenance on it. And in this system, you start seeing, hey, look at that, 82 in, 84 to the next unit. That means that the first box, the first MRU is full, should have been cleaned out. But in the beginning, whenever you put in a system, you always want to make sure you just let it go. Let it alone for a while. It'll tell you what the loading rates are going to be, and then you just determine from that, all right, there's my maintenance schedule. Sorry. Let's see. There we go. Okay, and this is one of the most important slides I think I've ever done before, where we're starting off. We've got the flow rate now on 526 flow rate, 80 gallons a minute. We had residence times of 18 minutes. That's the yellow, kilograms per day. So it was still removing 1.4 kilograms per day for both of those boxes. That's the entire treatment system. 4.8, approximately 5 cubic meters of treatment in total. So pretty small overall. 6.6, 35 gallons a minute, 2.7 kilograms removed, 42.9. But when we get into that 75 gallons a minute, oxygen is no longer a limiting factor. 4 kilograms, 2 boxes, 20 minutes of residence time. If you jump all the way up here to 8.2, to the point where it's starting to get clogged up, it's starting to get backed up, that first unit is pretty well full. It's starting to go into some of the overflow and over the overflow weirs. And you've got 58 gallons a minute, 25 minutes of residence time total, but you're still pulling 4.1 kilograms of iron in what is the equivalent of about 100 square feet. That's 100 square feet versus, in some other cases, acres of standard constructed wetland that needs to be built in order to achieve those same results. Just want to point out that going down into 913, I believe I had a good clean out by this point, but more leaves plugged up the front, 10 gallons a minute, 150 gallons a minute, or 150 minutes of residence, not even a kilogram for both boxes. So it really says it's not about going low and slow and giving it more residence time. It's about oxygen and the matrix, and of course, carbon dioxide availability as well. I took some samples then of the material because we didn't know exactly what it was. It looks like iron, and we took it up to the material characterizations lab in up at Penn State and Schwertmanite. So the 3 different sampling points that we had gone through, 1, 2, 3, or the first 3 or 4, was Schwertmanite, and then Goethite. But that last sample was taken from this pipe down here. So just because I just wanted to see what would be the long-term change. I just wanted to see if anything was going to change at all. And Goethite then, and I am no mineralogist, but Goethite is the older aged form of Schwertmanite or Jarosite. And if I'm wrong about that, please let me know either in the comments bar, questions or otherwise. But that's there's been a lot of research being pushed in that direction. Ms. Athena Chen, that's actually some of the things that she is working on figuring out is what are those rates of this brand new raw Schwertmanite, very hydrated, lots of water into it, and even some of the color forms that you can see if it's a bright orange or yellowish versus that darker burnt umber kind of color. I don't know how good of an indicator that is, but those are some of the things that I have at least seen as this material dries out and as I understand it then moves on towards the more stable form of Goethite. Won't say anything more about that though, not a biochemist. But moving along then, so those were our results from the first 2 years. Certainly encouraging. The MRUs by themselves were able to continue to demonstrate that yes, if you can get more oxygen back into the system with the right mix of organic matrix, and you know you've got carbon dioxide, and depending on the kind of material that you're using, whether you're using the metabolic pathways that are developing, whether they're lithoautotrophs or lithoheterotrophs, that the two working in conjunction can actually increase our overall treatment because, of course, as the lithoheterotrophs break down that material, they're producing carbon dioxide. So you're getting a double up. So if you, and there's even thoughts of, boy, if you can put something that breaks down more quickly down at the bottom of a treatment cell, and then it breaks down, it removes iron, and then it's releasing carbon dioxide, is that going to help increase the concentrations of carbon dioxide for the rest of the cell as it rises up in that vertical profile? Because remember, these boxes are vertical flow, bottom up treatment systems. So 2018, another self-funded system, but also with the assistance of Dr. Art Rose, Athena Chen, Dr. Peter Heaney, and of course, Anthony Taylor, my intern at the time. We were able to get another system put into place at a spot called KL1 Klondike by Asheville, Pennsylvania. So you can see myself, then Art, then Athena, and Peter is in the back there. He's kind of hidden by Athena a little bit. Anthony was taking the pictures.